And how do we describe, I mean, Rafael may have a deeper understanding of this, but for me, this is sort of a pragmatic point of view that, okay, this tells you a lot about quantum theory, but not everything. We need to put in an extra ingredient. And that ingredient goes by the name of the decoherence functional. Rafael mentioned it a bit. And just like the interference term, which is based on, has two, what is the word for it?
Arguments.
Arguments. Two arguments. It also is on two arguments. In particular, if A and B are single histories, then it is an argument on two different histories. Okay? So that's the object that we need. And so,
just
yes.
a point. So long what you have discussed, you just made the remark that it is not entirely the quantum theory captures. So you need a decoherence function.
yes. So in a sense, it's.
So in what? Can you just spell out a little bit?
So this isn't going to define for you everything about quantum theory.
So what do you mean by define everything?
So if I wanted to construct ordinary quantum amplitudes from this, I wouldn't be able to do it.
In a specific experimental context.
Unless I see it as arising, but it doesn't need to be. I mean, we know that there's. I mean, interference isn't the only thing you see in quantum mechanics, right? I mean.
Okay, discrete levels, discrete energy levels.
So I mean, how would you? I don't know. How,
Oh,
I'm not sure how to fully answer that
okay,
question.
Okay,
You know?
we will discuss later.
To me, it seems that you need this new ingredient, and what it does is it generalizes the structure. I2 is part of a larger object, more general object, and that's the decoherence function. Okay? So,
Yeah, but it depends what you want to do. If all you want to do is compute the quantum measure in the end, then this is the quantum measure. But if you wanted to look in the details of how you got the quantum measure, or if you want to look at extra axioms for the quantum measure, which are not written down here, then you need to refer to the decoherence function. So, as I mentioned the other day, if you had the quantum measure for some system and then some other system, and you were considering a composite system, and you wanted the quantum measure for that composite, it doesn't directly follow from the quantum measure for the separate system, but it does follow from the decoherence function of the separate system. And likewise, there's a positivity requirement there, but ordinary quantum mechanics satisfies a stronger requirement, which is called strong positivity, which can only be expressed in terms of the decoherence function, and not directly in terms of the measure. So a sort of capsule description of what's missing is that this I2 and the quantum measure has basically the real part of the decoherence function, as someone was saying. But the imaginary part of it is something extra that's not captured by the quantum measure. To the extent that the imaginary part plays a role, we need to talk about the decoherence function.
So I mean, if I think of just amplitudes as defined Feynman amplitudes.
So before you go, can you define now that you have a measure, can you not define an entropy right here?
You could. I mean, so I think. I think
It is von Neumann's formula.
Well, maybe.
Maybe you can.
So,
I think so, but I think.
It's attempting to try.
Yeah.
Yes, I
When
think.
with
Yeah, in
2
fact,
points,
this is a
there
set
are 2
of
points,
questions
there
that I
are
would like to be able to
there are
answer.
4 parts. So yeah.
So in fact, you could define this decoherence function, which I've just defined, as is very strongly reminiscent of the density matrix, and so therefore there's a lot within the structure that would suggest something like an entropy. And the question is whether you know how you make sense of it and so on. But yeah, let me just continue because I'll just not get through. I want to say at least a few words about coherence, because I do think this, to me, is a way in which this whole picture is completed, and even if some bit of that gets through, that will be useful. So anyway, but before doing that, I have to say a few words about the decoherence function. So if I think in terms of standard Feynman path, then, and I consider pairs of paths which are joined at the end like this, and Rafael said something about it, you can actually prove that in unitary theories this always has to be the case, just from standard quantum mechanics. I have a little proof here, but I'm not going to say it now, but you can, it's a very, I mean, even after, later today we can just quickly go over that proof. It's a very simple thing to show. But basically what this shows is that there's this object which is clearly not real, plus this complex one together, which gives you this real object. So this object is what I'm going to call a decoherence function. Okay? And in the case of, so in fact, what it also comes with is information about the initial state. And this is an important point, the state or the density matrix really at the initial density matrix at. Okay. So it's a sum, if you think of it, it's a summary of everything up to that point and then a statement about paths. Okay? So, so what are the properties of the decoherence functional? Just similar to this. So I'm just going to erase this. I choose here and say that. Sorry, I don't need to do that.
The definition it still has the H cross, right?
Yeah.
Yeah.
I mean, I circled the H cross to say that it's there, but it's not.
Oh.
I'm not putting it in.
Okay.
You're setting it
Sorry,
to 1.
I'm just setting it to 1.
Setting it to 1.
Yes.
Okay.
So again, this is now valued in the complex. So I've now generalized this object here, valued in.
So I gamma 2 define D.
I'm just okay. So what I'm going to say is that this is actually D of gamma 1, gamma 2. I mean, in this specific case,
Yes.
with these specific conditions, plus the complex conjugate.
So your D is just A gamma 1, A gamma 2? Or there's
Yes,
the minus sign?
minus sign A star, gamma 1.
A by...
But then with this delta function thrown in, so it's actually not just a product. It requires, it's not defined on all pairs. I mean, it's 0 on pairs that don't meet or define. So this is your decoherence functional. It's the thing that we're going to use to define the quantum measure. It has a property. We require of it various things. Instead of symmetry, you have that it's Hermitian. Okay. It is also biadditive, so it satisfies biadditivity. Okay. You may want to normalize it. You may want to say that d of omega equals 1. Okay. And there is one condition which is stronger, in fact, than just allowing complexity, allowing complex numbers, which is that of strong positivity. And one could keep this one even, but if you keep this condition, so strong positivity is a statement that if you give me a collection of events and I construct the decoherence functional on this, so I think of it as a matrix on this particular collection of events, then for every psi, and I'm writing it as a matrix on ij, where I mean d of ai, d of aj, d of ai, aj. This is a condition. Okay? So this, where did it come from? It seems a bit strange, but if you put this condition in, it turns out that you can reconstruct the Hilbert space of standard quantum theory. And I think this is actually a very...
What is psi here?
Oh, for all psi. For all vectors psi.
But this is a moment problem. You have put a condition like in a moment problem and reconsider the Hilbert space.
Okay. I need a lot of... What do you mean?
Hmm.
No, this I'm not right. I'm not doing anything at this moment to reconstruct. I'm putting in the
That means
section
all the
condition.
minors would be a positive. All the minors at
So
D.
in particular, it means that if I construct this matrix, then all its eigenvalues are positive.
Yeah, all the minors at okay. That
That
means Dij is the
positive
moment
left
of
and
a
the positive.
non-negative measure normally with x to the I, x to the j. This is there are these moment hamburger moment problem
Okay.
and so on. No?
I don't know. I don't know anything about them.
Okay. I read a Simon, for example,
Okay.
starts with this moment problem, reconstructs the Hilbert space.
So you can. So the whole construction of the Hilbert space is not. I mean, I think it was must have been obvious to Rafael right from the start, but it took a little while to reconstruct it in detail and to construct isomorphism between the standard Hilbert space and this one.
That I don't know.
But the construction is just essentially a GNS construction of this sort that Sachin talked about. So, but for that we're going to. I mean, I'm just saying too many words right now. So let me just try to be as specific here and just say that strong positivity allows you to construct from this history space, from this purely histories construction, the standard Hilbert space of quantum mechanics. And that to me is quite amazing because it suggests, at least to me, that the structures that you're talking about here are more general, or more fundamental.
This complex quantity, the D star, does it correspond to a time reversed part?
No, it isn't the time reverse because the final time is defined. That's where there is no. So that's the funny thing about this. Although it's unitary, there is at the final time is when the paths join up. But maybe Rafael has.
Well, in some sense, yeah, that's one way of thinking about it. Sometimes people will draw gamma 1, say, as a path going forward in time, and gamma 2 as a path going backward in time. As a convention, and then in
the
that case,
Schwinger, okay, you mean
the
in
Schwinger
terms of the
tells
Schwinger
us-
paths.
yes.
So you can draw it like this. So within this itself, one is going forward and one is going back. That's what you mean?
No,
Yeah.
I mean
Yeah, that's-
D and D star. D versus
Yeah,
D
so
star.
this in fact, here itself you can see is one path going up and one path coming down. And the other is reversed. The other path
So
is going up at
yeah,
time.
it's similar to what happened in influence function.
Yes, it's
Yes,
exactly that. That's
Exactly
exactly
that.
what it is.
Trees, yes.
Yes,
Schwinger
that's exactly what it is. The only confusion to avoid here is not to think that going backward in time means anti-particle. It's not it's nothing to do with particle
Right.
physics. And that's it.
Okay, so
Got
finally
so far
we're
as
in
time
coevents.
reversal.
I'll say a few words about coevents and then we'll stop. So coevents, which completes, sorry, I don't know how to use this. Completes this picture. So you see that so far what have we done? We've just taken classical stochastic theory and replaced the classical measure only with a quantum measure. Yes? That quantum measure satisfies a rule. Satisfies this particular rule, this quantum sum rule. It also can be derived from a decoherence functional like this, which allows us to define a Hilbert space. That's sort of aside, but this Hilbert space has another advantage, that it allows us to see this quantum measure, which just, for now we just said, well, it satisfies the sum rule, actually has a very well-defined mathematical definition as what is called a vector valued measure. Okay? And it takes values in the Hilbert space. An example of a vector valued measure is just on the real line, where it takes plus minus, and you can see already the quantum mechanics has that property. Things can be plus minus. And so this is the nature of the quantum measure. And that's all you've done. You've just taken that thing, replace it by another object. You're asking the same set of questions. You're not changing the sample space. Okay? Now, how are we to interpret things? I said a few words about this right at the beginning. And this is actually the trickiest part in some ways. And I think also, in some ways also not complete, because there are several open questions. as Rafael pointed out, there are schemes, some of which seem to work better than others, but we don't know why. And there's, in a very general sense, a question of how classicality can emerge and so on, but I'm not going to even go there. So as we said, classical probabilities need interpretation. So we have this idea of preclusion. And I just want to again go back to the classical case and say, well, how do I interpret the classical measure? What do I say? If I had a single history, so in a classical, like the classical random walk that I had, in any given realization, I have one particular history that is traced out. And I can ask, well, does it happen? And the answer has to be a yes-no answer. It happens, it doesn't happen. So there are truth values which are simply yes-no truth values. And all of this stuff in the classical case seems like an obvious and perhaps an overworked kind of way of explaining something we already know, which is very obvious. But that's to me what is really beautiful, is that you take the very obvious and you examine it in very great detail, and then if you generalize it, you're able to understand how to interpret quantum reality. Okay, and so I'm afraid I'll have to rush, but so what we're going to talk about are maps which take you from event algebras. Okay, and now the algebraic structure will become more apparent, just as Rafael explained, into the set Z2 of truth values. What is the algebra here? So, algebra in the sense that there's a linear operation and there's a multiplicative operation. So, we have the multiplicative operation, which is this. So, this is just 0, 1 with 1 plus 1. So, let me just write down the linear first. Sorry. Okay, just as standard here. And of course, we also have the multiplication rule. Okay. So, what you want are maps that take you from the set of questions to the set of answers. And the set of answers is simply yes, no. Okay? In a classical stochastic theory, this map, because it's between two algebras, and now let's go back to the algebraic structure here, we use the fact that, so addition, so this is defined as set difference, which is basically A without B, union B without A, symmetric difference, and AB, so let me just write that as a definition, is A intersection B. Okay? So this gives us an algebra, as Madhavan was asking, where is the algebra? And so now this is where we really need to use the details of this algebra. I think, maybe I'm mistaken, but this seems to be sort of the essential place to start with. Use it. So this is a map, but this is a map in classical theory which is a homomorphism. There are two algebras, and you want to retain the algebraic structure. That's what a homomorphism does. Okay? So this is the co-event phi. And the reason you call it a co-event is because it's a map from events to truth values. So such maps, like when you map functions or vectors, for example, you talk about covectors, mapping vectors into the reals. So in the same way you use the word co-event as a map from events to this particular algebra. So if it is a homomorphism, so classically phi is a homomorphism in particular and I will try to sort of give you physically what these things or logically what these things mean. So this is sort of the linearity condition, this multiplicative condition. So one thing that's important here is that
By
From
plus,
here-
do you mean the
yeah, I just
disjoint
mean,
union?
sorry, no, I just mean this, sorry. Let me just highlight this. This is very important. Can you see it?
It's a disjoint union.
No, it's a symmetric
Symmetric.
union. So you remove from A everything in B, then you add. So let me just draw it in pictures because I find that most useful. This is A and B. This is the. You remove basically the intersection. Okay, you have the intersections and then the stuff, the union without the intersection. Okay. So what this multiplicative rule tells you is that if I took omega and any set A which belongs to omega, okay, then I can write this as phi of omega phi of A, yeah? But phi of omega intersection A is just phi of A, right? And this is phi of omega phi of A. So if it was in fact true that A gives you a truth value yes, that's 1, then that means that this has to also give you a truth value 1. It cannot be 0. In other words, just this rule implies that, I mean, I'm not being complete in the sense that I haven't told you exactly that you can't have 0 events and so on, co-events and so on. So I don't want to make, at least something has to be true. Okay, some subset of omega has to be true. Okay, so, and this says something happens. Of course, it doesn't tell you very much because it tells you just something happens. Something happens, which is unlike what you can say in quantum, supposed to be able to say in quantum mechanics. Okay, so this is just a logical thing. And if you looked at this, then if A happens, then the complement of A doesn't happen. Okay, and these are things that we know about just standard classical logic, right? It's classical probabilities, right? This is something happens, its complement doesn't happen, and so on. That's how we interpret things. Point will be when we try to generalize this to a particular scheme, then what is it that you will keep? What are the kinds of logic you will keep? What is the kind of logic you'll throw away? Classical logic you'll throw away. So I'll try to finish in 10 minutes. So if just within the framework of a classical setup, you can ask, well, all these maps are possible, all these co-events are possible realities, but what is like a fundamental reality. How can you say that a particular path happens? Particular fine-grained history happens or not? And for this, we already use, without thinking about it, the idea of preclusion, exact preclusion, which is that if mu of A is equal to 0, the classical measure is 0, then implies that phi of A is equal to 0. In other words, that event does not happen. Yes? So we're using this, so we don't want coevents which are precluded. We don't think about coevents whose the language can get a bit hairy right now and tongue twisting, so I want to try to be as precise as possible. But this is one thing that you already have in classical theory, something you just sort of do without thinking about it. The next is that what you want to do is to say that really, so if I look at any one coevent, then I can look at the support of that coevent. That is one of the things you notice is that suppose I have a set A, which is yes, okay, which gives you a positive truth value, or yes truth value, then any set A prime which contains A also gives you a positive truth value, right? So there's in some sense a sort of hierarchy of sets, sort of a nested sequence of sets for a given coevent, and one wants to basically say, well, the smallest set associated with that coevent is what we call its support. Okay? And the notion of primitivity, which I just referred to a little while ago, is that you want to look at a coevent, a set of coevents which are not precluded, okay, which are which are preclusive in a, yeah, this is yeah, so it's so let me just continue what I was saying earlier, which is that you want to be able to look at something that is the most primitive, some coevent which has the smallest support possible. And in the case of classical theory, because of this homomorphism, that support, so the primitive, so-called primitive coevents, the things that actually happen are those which are the single history, so the ones that are at the bottom of this row. Okay? And of course, if you said that you had a very biased random walk and you said nothing ever goes right, yes? You had basically everything only has to go left to begin with, and we're just stopping at stage 2, then you just have those 2 paths rather than all 4 paths. 2 of them are actually set of measure 0. So I don't want them to actually, because 2 of them are a set of measure 0, those are not coevents with these as supports will always go to 0. So they don't happen. So the only possible coevents then are 1 or 2. Which is basically saying the obvious, which is that if you have such a biased random walk, then only one of 2 paths will happen. Okay? Now this is a very straightforward structure. Classically, now we have to ask the question, how do we generalize to quantum theory? So again, I think what is the beauty of this is that you don't generalize this, you don't generalize truth values. What you do generalize is the fact that phi does not any longer have to be a homomorphism. And that relaxation, so in other words, you don't have to satisfy both of these rules. So this is where the question of schemes comes in, because I could either choose to satisfy only this equation or only this equation. For reasons that are somewhat historical, I would say, and maybe depending on the various biases and prejudices of our group of people, we seem to like the multiplicative scheme the best. So I will stick with this. We just require that the quantum measure set that the coevents satisfy this condition. Okay? And this means, therefore, that at least something happens, and that's kind of nice. But what it doesn't mean is these two sets of things. It does mean the first, but it doesn't mean the second. In other words, so this is still correct. But this is now not correct. So in other words, you could have something as a set of measures. It does not happen, but its complement also does not happen. But then something happens.